All right, we are going over lesson 14 today on related rates. And I went over this briefly in a previous lecture, but I didn't go over it uh, as thorough as I wanted to. So let me tell you what related rates are. In this section or lesson, we look at questions that arise when two or more related quantities are changing. A good example is you're trying to find the area, how fast the area of a circle is increasing when the radius is a certain amount of meters with respect to time. The problem of determining how the rate of change of one of them affects the other rate of change of the others is called a related rates problem. And let's start with the first example. First few examples. Let me copy and paste them to our whiteboard. All right, the first question, we're not really working anything out. We just need to, with the given area equal to 5x squared, suppose that the dimension is x and the area formula is given of a particular shape, and they're differentiable functions of t. Write an equation that relates the derivative of a with respect to time to the derivative of x with respect to time. So all we need to do here, and by the way, dA over dt means the change in the area with respect to time, and dx over dt represents the change in the dimension of x with respect to time. So over here we have a equal to 5x squared. And we take the first derivative of both sides with respect to t. So the derivative of a with respect to t is the ratio dA over dt. And the derivative of 5x squared is just 10x. And because we're taking its derivative of x with respect to t, we must include the ratio dx over dt. So this first example was just to introduce you to how to take the derivative of a particular formula to get the various rates. Now, our second question goes back to implicit differentiation. So we got to use that again. Assume that all variables are implicit functions of time t. Find the indicated rate. We're given x squared plus 6y squared plus 6y equal to 36. And also dx over dt is equal to 3. In other words, the change in x with respect to time is 3. When x is equal to 6 and y is equal to -1, find the rate at which y changes with respect to time, or dy dt. So let's figure this out by implicit differentiation. Well, the derivative of x squared is just 2x. The derivative of 6y squared. Oh, let me back up just a second. Because we're taking the derivative of x with respect to time, we must include the ratio dx over dt. Now, plus the derivative of 6y squared is 12y. And because we're taking its derivative of y with respect to t, include the ratio dy over dt. The derivative of 6y is just plain old 6 dy over dt. And finally, the derivative of 36 is 0. Now, let's plug in all of our given information. X is 6. Dx dt is 3. Y is -1. And we leave dy dt alone because that's what we're solving. So this entire first part, that will give us 12 times 3, which is 36, minus 12 equal to 24. Let me backtrack for just a second. Let me make sure. 12 times 3 is 36. Okay, that part's fine. This minus 12 is attached to that dy dt. So I can't combine the like terms there. However, what I can combine that are like are the dy dt's. So 6 minus 12 would give us a -6 dy dt equal to 0. Now, at this point, you can either move the 36 to the right side or the dy dt part to the right side. I move the dy dt part to the right-hand side, and that gives us the equation now, 36 equal to 6 times dy over dt. Now, the last step, just like solving a regular linear equation, you would divide both sides by 6. Therefore, dy over dt is exactly 6. Are there any questions either off campus or on campus? Any questions here on campus? All right, let's look at the next example in our notes. Let's see. Hold on just a minute. Um, okay, I think this is the next one. All right, our next example. The original 24-meter edge length x of a cube decreases at the rate of 6 meters per minute. Part A, when x is equal to 3, at what rate does the cube's surface area change? And part B, when x is also 3 meters, at what rate does the cube's volume change? To answer or to even start part A, you would need to know the surface area formula for a cube. So we'll just do S equal to 6x squared. That is the formula to find the surface area for a cube. Now it says the original edge length decreases at the rate of 6 meters per minute. Because we're taking the derivative with respect to time, this is actually dx dt that we are given. Now, because it's decreasing, that means it's a negative rate, or negative 6 meters per minute. Now, let's take the first derivative of both sides of our formula. The derivative of s with respect to t is just ds over dt. And going back up here, at what rate does the cube's surface area change? That is ds over dt. That's what we're looking for part A. On the other side, the derivative of 6x squared is 12x. And because we're taking the derivative of x with respect to time, we include the ratio dx over dt. Now that we've taken the first derivative, we're ready to plug in our given information. We're given that x is equal to 3, so we plug that in here in place of x. And dx dt we're also given, that's negative 6. And when we multiply, we should get negative 216. And I believe the correct units are, since we're dealing with area, it would be meters squared per minute. Now, before we do part B, are there any questions off campus or on campus about part A?
No, sir.
Okay. Now, part B, at what rate does the cube's volume change? So the dx dt is still the same. And let's get the cube formula for volume. For a cube, the volume is V equal to x cubed. Now, what we're trying to find is at what rate does the cube's volume change with respect to time? And that is translated to dV over dt. Change in volume with respect to time is how you would translate that also. So let's take the derivative of both sides. The derivative of v with respect to time is dv dt. And the derivative of x cubed is 3x squared. And because we're taking the derivative of that with respect to time, then we need a dx dt after it. Now we are ready to plug in all of our given information. X is still 3, but we're squaring it. So we have 3 times 3 squared times dx dt, which is -6. Now, when we multiply everything together, we get -162. So the rate that the volume is changing with respect to time is -162 cubic meters per minute. Any questions about part B?
No, sir.
Okay. I think the next question on my notes also involves geometry. So let me grab the problem. Okay, here's our next question. When a circular plate of metal is heated in an oven, its radius increases at a rate of 0.04 centimeters per minute. At what rate is the plate's area increasing when the radius is 40 centimeters? All right, we're given a circular plate and radius, and also we're trying to find the rate that the plate's area is increasing. So we're going to use the area formula for a circle. Now, off to the side, I like to put my given information. The radius increases with respect to time, so that's the ratio dr dt, and its value is 0.04 centimeters per minute. We're also given the radius r is 40 centimeters. And what we're looking for is the rate that the plate's area is increasing. That translates to the derivative of A with respect to time. So that's the unknown that we're looking for. Now, going back to our area formula, take the derivative of both sides. So the derivative of A with respect to time is dA over dt. And the derivative of pi r squared with respect to time is 2 pi r, because pi is a constant. And since we're taking the derivative of r with respect to time, we need the ratio dr over dt. Now that we've taken the derivative, the next step is plug in all of our information. R is 40, and dr over dt is 0.04. Now, when we multiply everything together, we get 3.2 pi for our answer. And that will probably be square centimeters per minute. Now, if my math lab asks you to give an exact answer in terms of pi, then this would be the final answer. But if my math lab asks you to round your answer to a specific place value, let's say to the hundredths place, then on your calculator, you would hit your pi button. You wouldn't hit 3.14 unless it states so in the directions. So if you're asked to round, let's say to the hundredths place again, then your rate would be roughly 10.05 square centimeters per minute.
I have a question.
Yeah, go ahead.
How did you get the derivative of area over time? That's kind of where I kind of got lost at.
Oh, you're just taking the derivative of the area with respect to time.
Hmm.
So that's just dA over dt, just the change in area over the change in time.
So you're able to determine that from the wording of the word problem, or you just kind of know what to do?
Actually, both. That's a good question. Like if this had been c for circumference,
Hmm.
and you take the derivative of c with respect to time, then that would be the ratio just dc over dt.
Okay. Okay. And
Did that make sense?
yes, sir. And rate is another term for time.
Kind of. Rate is like your distance or change divided by time. You can look at it that way.
Okay.
Like in the change in whatever you're looking for, change in area, change in volume over your time, that's essentially what your rate is.
Okay.
It's like you're using the basic formula distance equal rate times time,
Mm.
but you're solving for the rate. So you would just divide both sides by t. So that's just kind of an informal definition of derivative.
Okay.
On campus, any questions here? All right, let me find another example for us to do. And I have not worked this one out ahead of time, so it May take me one or two times to get it. Okay, off campus, can you see that word problem with the ladder? Okay.
Yes, sir.
Okay, thank you. All right, a 15-foot ladder is leaning against a house when its base starts to slide away. The base being the X here. By the time the base is 12 feet from the house, which is also X, the base is moving away at the rate of 18 feet per second. So since the base is X and it's sliding away with respect to time, then that is known as our dx over dt. So that's 18. At what rate is the top of the ladder sliding down the wall? So for part A, we're actually looking for the rate that y or dy is sliding with respect to time. So dy over dt is what we're looking for part A. Our ladder forms a right triangle with the wall and the base. So we can use the Pythagorean theorem to get us started. So x squared plus y squared equal to, we'll just represent the ladder with the letter L. Now the ladder is constant. It's not going to change. So we can, with confidence, plug in 15 for L. We're given x is equal to 12, but we need to find y. We need to find the height of the wall. So let's find y first before we do anything else. 12 squared is 144 plus y squared equal to 15 squared, which is 225. Now to get y squared by itself, we subtract 144 from both sides. And that gives us y squared equal to positive 81. Normally, when we solve for a square, we take the square root of both sides. And normally we get two answers. We get in this case, a +9 and a -9. But since our height of the wall can't be negative, then we only say that the wall is 9 feet tall. So we can go ahead and label that as part of on our right triangle too. Any questions how we got the height of the wall?
No, sir.
Okay. Now we're going to use the same Pythagorean theorem with the same letters and also L being 15. We're still going to use that information to take our derivative. So let me erase some of this. All right, using our same Pythagorean theorem, uh, we're not plugging in x squared or y just yet. The only thing that is fixed or that won't ever change is the length of our ladder. So we'll plug in 15 squared there and still get 225. At this point, take the derivative of everything. And again, our independent variable is time. So to start, when we take the derivative of x squared, that is 2x. And because we're taking the derivative of x with respect to time, we need that dx over dt plus the derivative of y squared is 2y. And because you're taking the derivative of y also with respect to time, you include the ratio dy over dt. And on the right-hand side, the derivative of 225 is 0. Now we are ready to plug in all of our given information. X was 12. Dx dt is 18. Y we found earlier was 9. And dy dt is the rate we're looking for. Let me pause for just a second. Is everybody okay so far?
Yes, sir.
Okay. On campus, we're good? Now, I'm just multiplying 2 times 12 times 18. That gives us 432 plus 18 dy dt equal to 0. Now, I'm moving the 18 dy dt to the right-hand side, and it now becomes negative 18 dy dt. And just like solving a regular linear equation, you divide both sides by, in this case, negative 18. And your final rate for the top of the ladder sliding down the wall is negative 24 feet per second. And that makes sense because our ladder is sliding down. And in most cases, sliding down means you should have a negative rate or velocity. And remember, back in physics, you can't have a negative speed, but you can have a negative velocity or rate. Any questions again about part A?
No, sir.
Okay. Let me include this as part of our answers. And let's look at part B. Okay, part B. At what rate is the area of the triangle formed by the ladder, wall, and ground changing then? Our formula to find the area for a triangle is A equal to 1/2 base times height. But we're going to modify this and write it in terms of our x and y. The base is x and the height is y. And what we're looking for, it says the rate that the area is changing. So that means we're looking for the derivative of the area, or dA, the rate that it's changing with respect to time. Now let's take the derivative of both sides. The derivative of A with respect to time is the ratio dA over dt. Now on the right-hand side, because we have a product, we have to use the product rule. So the product rule is the derivative of f times g plus f times the derivative of g, where f is our 1/2 x and y is our g. So the derivative of f, or derivative of 1/2 x, times g, which is just y, plus f, or 1/2 x, times the derivative of g, or derivative of y. And keep in mind, we're still taking all of these derivatives with respect to the independent variable time. The derivative of 1/2 x is just 1/2. And because we're taking the derivative of x with respect to time, we have a dx dt here times our y plus 1/2 x. And the derivative of y with respect to t is just 1, but it's the ratio also dy dt. Are there any questions about the derivative?
No, sir. It's roughly the same concept as the last question, right? Example.
Yes, sir.
All right.
Now, at this point, let's fill in all of our given information. Dx dt is 18, y is 9, x is 12, and dy dt we just found to be negative 24. So when we do all the calculations, let's see, half of 18 is 9, times 9 is 81, half of negative 24 is negative 12, times 12 is negative 144. So the rate at which the area is changing is negative 63 square feet per second. And that makes sense if the ladder is falling and its length is decreasing as it's sliding down the wall, then that means the area is also decreasing. Any questions about part B?
No, sir.
On campus, any questions? Part C, let's figure it out. Part C, at what rate is the angle theta between the ladder and the ground changing then? All right, so the angle between the ladder and the ground is represented by theta in our picture. And the ladder and the ground, these are the two sides we're concerned about. Well, that is the adjacent, this is cosine actually, cosine of theta, because we have the adjacent side and also the hypotenuse. So our adjacent side is x. We don't plug in x just yet. Our hypotenuse L is a fixed number. So hypotenuse is 15. Now let's take the derivative of both sides. The derivative of cosine is negative sine theta. And because we're taking the derivative of theta with respect to time, we must include the ratio d theta over dt. Now on the other side, the x over 15, we can rewrite that as 1 over 15 times x. And that makes it easier to take the derivative of it. So the derivative of 1 over 15x is just 1 over 15. And because we're taking the derivative of x with respect to time, we must include a dx dt behind it. Now, let's plug in our given information. Dx dt is 18. D theta dt is our unknown. And we got another unknown. We don't know yet what sine theta is. But guess what? You can use your right triangle. Sine theta is opposite. Put this over here. Sine theta is opposite side over your hypotenuse. So our sine theta is actually 9 over 15. So replace sine theta with 9 over 15. Before we continue, is everybody okay so far?
Yes, sir.
How about here on campus? Any questions? Okay. All that's left to do now is just a little flipping and simplifying. So to get d theta dt by itself, let's multiply both sides by the reciprocal of negative 9 over 15. So we'll multiply both sides of our derivative by negative 15 over 9. Now a few things will cancel. 15 can go into its negative self negative 1 times. And 9 can go into 18 2 times. So the rate at which our angle is changing with respect to the ladder and the ground in terms of time is exactly negative 2, whatever units MyMathLab gives you. I want to say radians per second, but again, MyMathLab will, if I remember correctly, will supply the units for you. Are there any questions about this particular problem?
No, sir.
Now, there are some questions I have not or will not go over from the homework. So when you run across those, if you have any questions, just reach out to me through my email or through the Ask My Instructor help tool.
How long does it take for you to see when we ask for help with the homework with the tool?
Usually I answer if it's during the day I'm not in class, I answer right away.
Okay.
If it's at night, if it's late at night, I usually answer first thing in the morning.
Okay.
So it's within, no, it's nothing like 2, 3 days later. I will answer it in a timely manner while I'm not wasting your time.
All right.
I want to go over one more example with you guys. And let me see if I can find it. I think it was another. Oh, here it is. I'm sorry, I kept skipping over it. All right, let me screenshot it and put it on our whiteboard. Okay. On both campuses, can you see this okay?
Yes, sir.
Okay. Can you see it okay here? I'm sorry I stretched it out a little bit. All right, a spherical balloon is being inflated so that its diameter is increasing at a rate of 2 centimeters per minute. How quickly is the volume of the balloon increasing when the diameter is 10 centimeters? First thing we need to find is what formula we're going to use. Uh, the volume of a sphere is V equal to 4/3 pi times your radius cubed. Now we need to, because we're given the information about the diameter and not the radius, we know that the radius is half the diameter. So in our formula, let's replace R with 1/2 times D. Again, I'm only doing that because we're not given any information about the radius. We're only given information about the diameter. Now, let's put our given information over here to the side. The diameter is increasing at a rate of 2 centimeters per minute. So the change in the diameter with respect to time is 2 centimeters per minute, or dd over dt. You're also given that the diameter is 10 centimeters. How quickly is the volume of the balloon increasing when the diameter is 10 centimeters? Our unknown rate is the volume increasing with respect to time is the ratio dV over dt. And let me use a lowercase d so that way we know it's the diameter. Now, before we take the derivative, let's take that 1/2 d and raise it to the third power. So that will give us 4/3 times pi. 1/2 cubed is 1/8 d cubed. And we can cancel, 4 can go into 8 2 times. So the right-hand side simplifies to 1/6 times pi times d cubed. Now we're ready to take the derivative of both sides of our formula. The derivative of v with respect to time is the ratio dv over dt. On the right-hand side, when we take the derivative, we move the 3 to the front and multiply it by the 1/6 pi. And we still subtract 1 from the original exponent, giving us d squared. Now, because we're taking the derivative of the diameter with respect to time, we must include the ratio dd all over dt. Let's simplify a little bit in front before we continue. 3 can go into 6 2 times. Now we are ready to plug in our given information. And let's leave our answer in terms of pi. So we have dv over dt equal to 1/2 times pi. We are given the diameter, that's 10, and we are squaring it. And we are given the diameter rate when it's increasing with respect to time. So dd over dt is given to be 2. Now we can cancel out the 2's. Uh, 10 squared is 100 times our pi. So our volume, the volume of our balloon is increasing at a rate of exactly 100 pi cubic centimeters per minute. If my math lab wants an answer, a decimal answer, rounded to a particular place value, then you would just mash the pi key on your calculator. And let's say we wanted our answer to the 10th place. So that would be roughly 314.2. Again, don't use 3.14 for pi. In most cases, you would need to hit the pi button on your calculator. Are there any questions about this word problem?
No, sir.
Okay, I think I've given everyone enough examples to go by. Um, Again, if you see a question I didn't go over in class that I've not already removed, just email me or you can use the Ask My Instructor feature and I'll get a direct link to the question.